A binomial random variable counts how many times a particular outcome called success occurs in a fixed number of independent trials. Each trial has only two possible outcomes, success probability p or failure 1 minus p. If we denote the number of successes by x, then x can take integer values 0, 1, up to n, where n is the total number of trials. The probability mass function PMF gives the probability that x equals a specific value k. Px equals k equals n, choose k times p to the k times 1 minus p to the n minus k for k equals 0, 1 up to n. The factor n, choose k, counts the different ways we can choose which k trials out of n are the successes. Think of tossing a fair coin 10 times and asking how many heads appear. The number of heads follows a binomial distribution with n equals 10 and p equals 0.5. Explanation: for a real-world experiment to be modeled by a binomial distribution, 4 key conditions must hold. 1. Fixed number of trials n. The experiment is performed exactly n times. Example: 20 quality control inspections on a production line. 2. Two mutually exclusive outcomes per trial. Each trial ends in success or failure only with no third option. Example: a component either passes the test success or fails failure. 3. Constant probability of success p. The chance of success does not change from trial to trial. If the machine is calibrated and the environment stays the same, p remains stable. 4. Independence of trials. The outcome of one trial does not influence any other. In the coin toss example, knowing that the first toss was a head tells you nothing about the second toss. If any of these conditions is violated, the binomial model may give inaccurate probabilities. To find the mean expected value of a binomial variable x tilde bin of np, we start from the definition. E of x equals sum from k equals 0 to n of k times p of x equals k equals sum from k equals 0 to n of k times n, choose k times p to the k times open parenthesis 1 minus p close parenthesis to the n minus k. A neat trick is to view x as the sum of n independent indicator variables. X equals sum from I equals 1 to n of I sub I, where I sub I equals 1 if the ith trial is a success, and I sub I equals 0 otherwise. Because each I sub I has E of I sub I equals p, the probability of being one linearity of expectation gives. E of x equals sum from I equals 1 to n of E of I sub I equals sum from I equals 1 to n of p equals np. No matter how large n is, the average number of successes simply equals the number of trials multiplied by the success probability. For a concrete analogy, imagine a basketball player who makes each free throw with probability p equals 0.8. In 100 attempts, we expect on average 0.8 times 100 equals 80 successful shots. The variance measures how spread out the binomial outcomes are around the mean. Using the same indicator variable representation, we first compute the variance of a single indicator. Var I equals p, 1 minus p, because I is a Bernoulli p variable. Since the indicators are independent, variances add. Var x equals sum from I equals 1 to n of var I equals sum from I equals 1 to n of p, 1 minus p equals np, 1 minus p. Another way, starting from var x equals e of x squared minus e of x squared, leads to the same result after algebraic manipulation of the PMF. Intuitively, when p is near 0 or 1, the outcomes are less uncertain, variance small, while p equals 0.5 gives the largest spread because successes and failures are equally likely. Worked example: suppose a manufacturer inspects 50 widgets, and each widget is defective with probability p equals 0.02. Let x be the number of defective widgets. Mean: E of x equals np equals 50 times 0.02 equals 1.0. On average, we expect one defective widget per batch. Variance: var of x equals np left parenthesis 1 minus p right parenthesis equals 50 times 0.02 times 0.98 equals 0.98. Standard deviation: square root of 0.98 approximately equals 0.99. Thus, most batches will have 0, 1, or maybe 2 defective items. If we wanted the probability of exactly 3 defectives, we would plug k equals 3 into the probability mass function. P of x equals 3 equals combination of 50 choose 3 times open parenthesis 0.02 close parenthesis cubed times open parenthesis 0.98 close parenthesis to the power of 47 approximately equals 0.0035. A small chance indeed. The MGF of a random variable x is m sub x of t equals e of e to the tx. For a binomial x tilde bin of n comma p, using independence of the indicators, m sub x of t equals e of e to the t sum from I equals 1 to n of I sub I equals product from I equals 1 to n of e to the t I sub I. Each I sub I is Bernoulli of p. So e of e to the t I sub I equals 1 minus p times e to the t times 0 plus p times e to the t times 1 equals 1 minus p plus p e to the t. Therefore m sub x of t equals 1 minus p plus p e to the t all raised to the n. The first derivative of the MGF at t equals 0 gives the mean. M prime sub x of t equals n times 1 minus p plus p e to the t raised to the n minus 1 times p e to the t. So e of x equals m prime sub x of 0 equals n times 1 minus p plus p raised to the n minus 1 times p equals np. The second derivative yields e of x squared. M double prime sub x of t equals n times n minus 1 times 1 minus p plus p e to the t raised to the n minus 2 times p e to the t squared plus n times 1 minus p plus p e to the t raised to the n minus 1 times p e to the t evaluating at t equals 0 gives e of x squared equals n times n minus 1. P squared plus np equals np times 1 minus p plus np squared. Finally, variance equals e of x squared minus e of x squared equals np 1 minus p. This compact MGF proof is favored in examinations because it avoids summation tricks and demonstrates mastery of generating functions. Explanation: common pitfalls. Mixing up n and np, the formula for variance uses both n and p. Not just the mean np. Forgetting the 1 minus p factor leads to overestimating spread. Assuming independence when it does not hold. If trials influence each other, for example drawing cards without replacement, the binomial model is wrong. The correct distribution is hypergeometric. Using the wrong p, sometimes p refers to probability of success defined by the problem statement. Swapping success and failure flips p to 1 minus p and changes mean and variance. Applying the formula for non-integer n must be a non-negative integer. Fractional trial counts are meaningless. Forgetting to multiply by the combinatorial factor when computing probabilities manually. The n choose k term is essential. Rounding errors in calculators. When p is very small or very close to 1, computing p to the k times 1 minus p to the n minus k can underflow. Using logarithms or software with high precision helps. When the number of trials n becomes very large while the success probability p becomes very small, but the product lambda equals np stays fixed, the binomial distribution approaches a Poisson distribution with parameter lambda. Limit as n goes to infinity and p goes to 0, and np equals lambda of n choose k times p to the k times open parenthesis 1 minus p close parenthesis to the n minus k equals e to the minus lambda times lambda to the k divided by k factorial. For k equals 0, 1 dot dot dot. The Poisson model is easier to work with because its probability mass function involves no large combinatorial numbers. In practice, engineers use this approximation for rare event problems, such as the number of system failures in a huge fleet of components, where each component fails with a tiny probability. For example, if a network has 10,000 links and each link fails on a given day with p equals 0.0001, then lambda equals np equals 1. The probability that x equals 3 is approximately e to the minus 1 times 1 to the 3 divided by 3 factorial, equals 0.0613, which is much simpler than evaluating the full binomial expression. The approximation works well when n is greater than or equal to 20 and p is less than or equal to 0.05. Otherwise, the exact binomial should be used.